So I'm Kate. I'm an assistant professor in the Department of Geological and Environmental Sciences. And I'm what we call a geochemist, which means that I study the chemistry of earth materials, how fluids and rocks interact. It's a pretty broad area. And so my particular area of expertise is in what we call reactive transport. And this is thinking about what happens when fluids are moving and reactions are happening simultaneously. So it's sort of like chemical engineering of rocks and minerals and earth materials. So it's a really fun area to work in. I love it. And one of the things that I love about it is that we work across really broad scales. And so the figure on the left-hand side there is actually a picture of a basin that contains oil and gas. That's a seismic image of a basin at scale of hundreds of kilometers. The picture in the middle is actually at the scale of nanometers. This is actually a mineral surface that's been exposed to CO2, and we're trying to understand the reactions that happen. And then on the far right is a really interesting example. It's about the size of my fist, and I forgot to bring it. I meant to bring it, but it's actually a rock that's been turned entirely into CO2, which is amazing. So it's a mineral called magnesium carbonate, and I'll talk about it in a second. And so we've had a couple of projects going in the broad area of carbon sequestration. We had a GSEP-funded project which looked at the idea of mineral carbonation in particular, and this is reacting CO2 with minerals to form carbonates. We also did a little bit of work in the course of that project on the idea of abiotic CO2 reduction, so turning CO2 back into different types of hydrocarbons. And finally, we looked a little bit at saline aquifer storage and different engineering strategies to help turn the CO2 into mineral forms to keep it from leaking back to the surface. So we've had kind of a broad array of topics. I thought just to sort of get us going on this idea, we would start off with a little fact-checking. And so this is a quote. It was released back in May, one of my favorites of the most recent array of wonderful quotes in the news. But this was from our esteemed representative, David McKinley, who was the head of the House Science Committee, and this quote came out right about the time when the Pentagon, when the House decided that they should forbid the military from thinking about the effects of climate change. So probably symbolic, but it was an interesting vote. And so his quote here that we're going to sort of analyze was that climate change alarmists contend that man-made CO2 is the cause of climate change. Most people may not realize that 96% of all CO2 emissions occur naturally. So just let's take a poll here and see what you guys think. True, false, or I have no idea. So true, raise your hand. We have which one true? It's okay, your professors aren't here. We have some trues. Everyone's going true.
We're talking about the effort that is so big that
yeah, exactly.
makes a difference.
That's what makes a difference.
So true, false, or I have no idea. You guys are pretty good. You do better than most audiences do. So to understand, I'm going to trip over this chip. I'm just going to move it. To just understand this question a little bit, there's a really interesting point that emerges about how the carbon cycle works. So this is just your average carbon cycle diagram. And what's shown here, the blue numbers are the sizes of the reservoirs in petagrams of carbon, so 10 to the 15 grams of carbon. And the red arrows are showing the fluxes between the reservoirs. So quickly we can start to get a handle on whether this representative was telling the truth. So we have plant respiration and soil respiration that are returning carbon to the atmosphere, and photosynthesis, which is taking up CO2. And so those two about equal each other out. They sort of cancel out in terms of net CO2 from the biosphere. Then we have volcanoes, which emit a small amount of CO2, land use change, and fossil fuel burning. So if we add those up, we get something like, 7 petagrams of carbon per year. And then we can look over at the ocean. The ocean's also approximately in equilibrium with respect to CO2 exchange. There's a little bit of an imbalance now that's driven by the perturbation to atmospheric CO2. And then we have this huge reservoir of the ocean, which receives some CO2 from rivers, mainly in the form of bicarbonate. And then this bicarbonate is transferred into the sediments and permanently buried. So that's kind of the breakdown we have. So if we sort of add up the natural carbon cycle before humans came into the picture, we can think about the change in carbon in terms of the net flow into the atmosphere and the net removal. And if we do that, we see that volcanic emissions are really the only net source of CO2 that we have, and that's about 0.1 petagrams of carbon per year. And the only removal sink we have to get carbon out of what we call the surface reservoir, which is the ocean and the atmosphere, is 0.1 petagrams per year in sediment burial. And so these balance out, so we have no change in carbon. If we add in humans, we see that the fossil fuel burning plus the land use change is about 7 petagrams of carbon per year. So it turns out that human activity is roughly a factor of 70 over increase in net carbon to the atmosphere over the background state, which is an astronomically big number if you think about it. We have never seen an abrupt change of that magnitude in Earth's history, and we've seen some pretty abrupt changes. So this is a remarkable one that is happening today. So going back to the question of whether our congressman was telling the truth, he was, but he was exploiting the difference between net and gross fluxes. And so 96% gross is true. But when you look at what the actual implications are of that tiny net, that 4%, I don't know who it was that said that, it's really big. So I like to think of this as we're basically emitting CO2 at 70 times the speed limit, which is probably something like, I don't know, what is that, 5 times the speed of sound or something. So it's a really astronomically high number. Are you guys interested in hearing about how Earth has done this, how managed carbon over geologic timescales? You are? Okay, I'll say a little bit about it. It's a pretty fun story. So the idea for Earth's moderation of the carbon cycle was developed by actually a mining engineer in 1878, and then it was capitalized on by Urey in about 1948. And this reaction is a reaction between calcium silicate, so this is a rock-bearing mineral, and CO2. And the CO2 is either in the atmosphere or in the soil environment derived from plants. And through the breakdown or dissolution of these minerals, in the presence of CO2, we transfer alkalinity, bicarbonate, to the oceans where we precipitate limestone and quartz. And that permanently removes CO2 from the atmosphere. So why don't we run out of CO2? We have volcanoes, we know, that are emitting CO2. If we actually look at how this process works, it's governed by this sort of effective rate constant we'll call a K. If we look at how this works, it's actually a stabilizing negative feedback that keeps carbon concentrations in check. And so we can write a really simple equation. Obviously, we use big models to predict this today, but we can write a simple mass balance statement that says the change in carbon in the ocean atmosphere system is equal to the production from volcanoes minus what comes from silicate weathering. And you see this dependence on climate. That's because when it's warmer, you weather things more quickly, and that removes CO2 and keeps the system in balance. So it's a very classic stabilizing feedback that has operated over million-year timescales to keep atmospheric CO2 levels fairly constant. And this is just a plot showing atmospheric CO2 over the last 60 million years. It's quite a long time span. So we're down here today. But times, for example, the Eocene period, we had quite high levels of CO2. We don't know exactly how high because we don't have a way to measure directly. We use proxies. But up to, possibly as high as 1,000 to 3,000 ppm CO2. The reason why we know that this works is shown here. This is some modeling that one of my students just did, actually looking at the long-term carbon cycle balance. And what he's been able to show is that over million-year timescales, despite large changes in CO2, the atmosphere has actually stayed in balance. And that means that this feedback has been strong enough to stabilize carbon. The problem with this, if you remember back to the size of these fluxes, is it's very small. And so it only recovers from perturbations to CO2, such as we're imposing today, over about 100,000 year timescale. So it takes a while to get that carbon out of the ocean atmosphere system because of this process. So that's kind of the geologic perspective on what we're doing today. And I'll just mention there's an interesting period right here at the Eocene-Paleocene boundary called the Paleocene-Eocene thermal maximum, and it was a time very analogous to today when massive quantities, about somewhere between 1,000 and 5,000 petagrams of carbon were released to the atmosphere. Warming was about 3 to 5 degrees C, and it resulted in massive ocean acidification and several major extinctions. So it was a really profound interval that's very analogous to today. Yes?
So couldn't the climate skeptics use this chart
They do all the time.
Yeah. So like, how do we?
And the important
come out
point,
of
the
that?
really important point is that these are unfolding over million-year timescales. And if we want to wait 1 million years for the perturbation from anthropogenic CO2 to go away, then it probably will be absorbed and redistributed by these natural processes. But the rate of change that we're imposing today is just so much faster. It's faster than anything we've seen. Yeah.
What led to the spike in the carbon in genes that you were given that is identical to what we have right now?
Yeah, it's debated. I don't think we know exactly. There's a lot of different possible causes. One of them is destabilization of methane clathrates, and released a bunch of methane to the atmosphere. It's a wide range of ideas from volcanic eruptions, so I don't think the exact causes are known.
Do you have info on temperature or extinctions during that massive excursion?
The problem with it was that there was so much ocean acidification that we lost the carbonate record that we would normally use to reconstruct what happened. So they're working on developing better reconstructions and better records for that time period. I think the estimates now are between 3 to 5 degrees C. And so, but it was a pretty major event. Yeah.
Just a curiosity, is it possible that if you have like a few volcanic eruptions, they lead to a chain reaction between volcanoes or make
No.
It's not related at all? Like
No. I mean, you have plate boundaries which control where the volcanoes exist. You know, but if you think about like the implications of this, 70 times as much CO2 emissions, you would have to take a volcanic chain the size of the Cascade Mountains, which go through most of Oregon, Washington, and up through parts of British Columbia, and put 70 of those on the continent. So we would have to turn the whole world into volcanoes, basically. If that helps. Yeah.
And can you just talk a little bit about ocean acidification and just like what the effects are between the atmosphere and ocean acidification?
Oh boy, okay. I'm not a marine geochemist. There are much better people like Ken Caldera who thinks a lot about this. I'll do my best, and if I say anything wrong, someone will have to correct me. So as you know, the ocean has a fairly complicated buffering system. We have a lot of calcium carbonate there. So as you increase CO2, some CO2 partitions into the ocean, which reduces the alkalinity, and eventually you hit a point where you undersaturate with respect to calcium carbonate, and so you start dissolving calcium carbonate. And that's the real concern today over loss of coral reefs and calcifying organisms in surface oceans. Eventually, that's not sustainable, and you'll start to redissolve pre-existing or older calcium carbonate, and you'll probably return the system. But again, that's a really slow process relative to, you know, the increase in acidity that's coming from dissolution of CO2 into the ocean. Is that?
Yes, that's like, is it kind of a similar process to like the weathering that happens in limestone buildings due to
Yeah, sort of.
like acid rain, right? Like if there's
Yeah. Basically, yeah, you're creating conditions in the ocean where calcifying organisms can no longer create a driving force to create their shells. And so their shells actually start to dissolve, or they just can't create new ones. They're seeing this now in some mollusks. They can actually create shells effectively. So yeah, it's a similar idea. And so the key there is if we could get more alkalinity into the oceans, that would help. Yeah.
I think that the oceans, I've heard, are taking up more CO2 than anyone can understand why they are, that there's this extra reservoir that's sort of saving us, but nobody quite understands. Can you talk about that?
I don't know very much about it.
Okay.
Yeah, I couldn't say anything.
But is that the claim?
Yeah, I think there's a couple of issues there, and that one, that the missing CO2 sink is now, I think some people are also thinking it might be on land, is my impression. And part of the issues with the ocean might be that we didn't have a good understanding of temperature, but I don't know very much about it. That's kind of off the top of my head from what I've heard. Okay, so that's the geologic story here. And so what I've just told you basically is that the Earth has some ways that are pretty effective at storing carbon. And if you look at this diagram, you can see that if we put it into the oceans, there's a lot of storage there. The Earth's crust is astronomically big. Much of that is calcium carbonate that's been stored. And then we have fossil fuels, which are a relatively small reservoir. But we can kind of use these to tell us where we should put carbon. So one option is to store carbonate minerals. That would be the most stable form of CO2 in the environment. The next would be to store CO2 as organic carbon in reducing sediments, because if it's organic carbon, such as biomass from agricultural activities, is unstable in the soil. There's lots of little organisms that view that carbon as Twinkies and want to oxidize it and eat it. So we need to put organic carbon in reducing environments if we want to keep it there for a long time. And then the third one is probably gas, CO2 stored as a gas in subsurface reservoirs. And we have many natural examples. In fact, they're mined today for CO2, where CO2 has been stored in the equivalent of oil and gas reservoirs for tens of millions of years. And this idea, this isn't the best figure, this is just kind of getting at that conceptual idea that, so here's CO2 with zero enthalpy, and the amount of energy to create any of these reduced forms of carbon is roughly about what you would get from burning it. So you don't really gain anything by turning carbon back into other forms. And then if you react CO2 with minerals, these are a bunch of different minerals, these reactions are actually exothermic, and you end up with a more stable end product than going the other direction. So in terms of what we can do now technology-wise, I like to think about our geoengineering strategies for the subsurface really in terms of kind of three main things. So how big, how much can we put down there? We've got the 7 petagrams of carbon per year that we have to deal with. That is just a huge number. How long can we keep it there? It doesn't do us a lot of good to put something down in the ground and have it come back up 10 years later. And then, when can we do it? Is it something we can do today? Is it something we have to do 50 years from now because we just don't have the technology? And then there's kind of this how much question. And this comes back to your question. And I would say that, most of these strategies that are talking about large-scale carbon storage in the subsurface are, far off, at least are on the very far right-hand side of the McKinsey curve, which is to say that we're looking at maybe $60 to $100 per ton of carbon to sequester it. It's very expensive. And I'll talk about some of the reasons for that. So I'm going to talk about the one we can do now, which we can pump CO2 into the subsurface and we can hold it there. And sometimes we can use it for enhanced oil recovery. And I think it was someone in this group that mentioned, is CCS just a way to keep us reliant on fossil fuels? Is it, not necessarily solving the problem? And I want to talk about that because I think it's a really good point. And then CO2 into minerals, so forming minerals. You can do this either above the ground or beneath the ground. And then there's this idea of enhanced silicate weathering, and this is basically flying airplanes around the world and sprinkling minerals on the Earth's surface to basically stimulate this natural weathering process that we talked about earlier. So this is sort of arranged in terms of how big and when. And then the one that I've been kind of interested in, and we've had some success, is the idea of putting CO2 into the subsurface and using the natural chemical potential of the subsurface to turn it back into organic carbon. And it's kind of a crazy sort of pie-in-the-sky idea, but I think it's a really interesting thing to think about, and not necessarily crazy, totally crazy at least. So for those of you who aren't familiar with how geologic carbon storage works, it really consists of 4 steps. And so the first step is the capture step. And so if we're looking at a fossil fuel power plant, and really CCS is only thought to be even mildly technologically feasible at stationary fossil fuel plants because you need this gas stream to capture the CO2. And so capture, I know less about capture. There's a woman here named Jen Wilcox in energy resources engineering who does a lot of work on capture. But if you think about what has to happen, you basically need to have some sort of sorbent that will take the CO2 out of the gas stream, and then you have to get the CO2 off the sorbent. So it takes heat, there's some degradation of the sorbent over time. So this is where the big energy penalty comes in, and it can be as much as 40 to 60% energy penalty on the plant for CO2 capture. So it's a really big number. And DOE has been really pushing to bring this down, but it's been one of the big cost and efficiency barriers. So after we capture the CO2, we compress it into pipelines and we pipe it to the place where we want to inject it. So we have a significant component of pipeline transport. And when you start to think about the scale, we're talking about these multiple petagrams of carbon. It takes a lot of pipelines to move them around. But technologically, we have experience with all of these. The oil and gas industry is really good at piping things. They're also really good at putting things underground and taking things out of the ground. And so the idea for geological sequestration is to pump the CO2 down into the subsurface. And you can see that we have these like weird clouds of CO2 on these diagrams. And that's because CO2 is in a supercritical fluid when we pump it underground, and that allows us to get a lot more fluid underground as opposed to storing it as a gas. So in terms of how much, we have a lot of storage capacity for CO2, and this is just focused on North America, and I'll show you some maps of where this is happening worldwide. So we can put oil and gas, we can put CO2 into depleted oil and gas reservoirs. We've already taken the oil and gas out. So in terms of US numbers, I think 60 years worth of US supplies is about 140 gigatons of CO2, so it's a big number. It's about 60 years worth of our current production rate. Unminable coal formations are another place that people talk about. That's about 80 years of storage capacity for the US. And then saline aquifers, which are basically very, very deep subsurface aquifers that have water that is not at all fit for human consumption. This is water that is 10 to 100 times more saline than seawater. So not something you would ever drink, but there's a lot of storage capacity you can see going through, especially parts of Canada and the Gulf Coast, huge amounts of storage capacity. Yeah.
Oh, I was going to ask, how would you store CO2 in, for example, an unminable coal formation? Is there enough permeability to store?
Yeah, that's a good question. The thought is yes, but these are generally lower porosity permeability rocks. So yeah, it's a good point. Most of these, some of these are carbonate. A lot of these are carbonate reservoirs that have a lot more porosity. Yeah. Is there another?
No, that's fine.
Okay. So just to have a phase diagram and a talk about CCS seems important. This is the phase diagram for CO2, and this is pressure, temperature, and these are the temperature gradients for a warm basin and a cold basin. So, most of the US would be somewhere in between here. And at the pressures we're thinking of injecting, here's the critical point for CO2. And most places we're thinking of injecting are somewhere around in here. So, 100 to 150 bars and temperatures between 80 to 100 degrees C. So in this case, we're dealing with a supercritical fluid, which is interesting because it allows the CO2 at that phase is more buoyant than water, so it comes up and it nestles against the top of the reservoir, which means that we need to have some sort of impermeable layer at the top of our aquifer to stop the CO2 from migrating further up. And this is just shown in a very schematic way here. So here's what we call a seal, or this cap rock that's an impermeable unit, like a shale, if you guys know about shales, that's stopping transport. Here's our well. We're injecting CO2, and the blue is showing the supercritical CO2. Over time, that CO2 dissolves into the water, and as the CO2 dissolves into the water becomes more dense, and you get this sort of convective flow that continues to aid in dissolving the CO2 into the water. So if we look at what we call the trapping contribution, which is how much CO2 has been stored, or how safe that storage is since we've injected it. Initially, we're just relying on the structural and stratigraphic trapping, so this seal that stops anything from moving upwards. And over time, we get residual trapping, which is CO2 that's stuck in capillaries, and then finally the CO2 dissolves, and then finally, in some places, we might start to form minerals if we have the right rocks. Yeah?
You said CO2 is less dense than water.
Mm-hmm.
How does, if you dissolve the CO2 in water, why would water become more dense?
Why would the water become more dense?
You said because after the CO2 has dissolved.
Yeah, because you're adding the CO2 to the water as it dissolves, so you're changing the density slightly, so you get this sort of convective flow. Yes, and so you can imagine most of the subsurface is not composed of a flat gray rock. We have faults and different things that occur in these reservoirs, and we have to know they're there to keep the CO2 down. Oops. Apparently I animated all of the different features here. Get through that. And so this is now getting back to the question of, characteristic storage time versus storage capacity. And there's a lot of lines and things on this diagram. I just want to draw your attention to a few of them. So here's what I mentioned earlier. The issue with soil carbon is that we could potentially store a decent amount of it, but it doesn't stay stored for very long. Here's underground injection. So we have a huge storage capacity, and we think it'll stay there for maybe, tens of thousands of years, which is pretty good. And then we can go up to this feature we call mineral carbonates, which has both a massive storage capacity and a really long characteristic timescale. And I'll say a little bit about, what are the technical challenges with CCS right now. A lot of it relies on physical trapping. So, we have some understanding of multi-phase flow. We need a better understanding. A lot of people are working on having better models to understand how the CO2 goes in and reacts with the fluids. Geomechanics is a big deal. We've had one CO2 injection site shut down because of induced seismicity and leakage of the CO2. So understanding how the overpressurization that comes from injecting CO2 changes the subsurface is another big area of research. And that ties into reservoir characterization. So they use seismic imaging to actually detect faults, but seismic doesn't have a very high resolution, and so you can still get leakage up, small faults and things like that. And then finally, if we do have a leakage event, what do we do? And it turns out that it's actually pretty easy to stop CO2 leaking. You just need to pressurize from above, and you can push the CO2 back down. So those are some of the challenges. The other challenge on the chemical trapping side is that most sedimentary rocks and waters don't have a lot of divalent metals, and that's what we need to make the carbonates that permanently lock up the CO2. And the timescales over which minerals tend to precipitate are pretty slow relative to the timescales we're interested in. But I would say overall, these are somewhat, I won't say they're minimal problems, but they're problems we have a pretty good handle on. It's really a mature technology that I would feel comfortable if someone wanted to put CO2 underground in California. What are the real challenges? We've talked about this a little bit. The price of CO2 capture is still really high. So right now we're around $60 a ton. DOE is hoping to get it down to $40 a ton. That's sort of the goal. Long-term site management, if you think about putting a lot of CO2 underground, most people would want you to have some sort of insurance for the next 100 to 1,000 years, that if anything goes wrong, there's going to be somebody there to actually fix the problem. Sort of like Yucca Mountain, when we wanted to put nuclear waste at Yucca Mountain, they wanted the site performance. Originally, it was supposed to be, I think, 10,000 years, and then it was up to like 100,000 years that they had to be able to demonstrate that the waste would stay there, and the same thing is sort of happening with CO2. So that's one of the other issues with cost, is this long-term site management. You need future planning, the pipeline transport requirements, and then really, this touches on what you guys were saying, there's no economic incentive to undertake such a costly measure. So that's been the real barrier to seeing CO2 happen. And then there's also been a backlash. I think some of this comes from what's happened with fracking, where, there's an interest in what's happening in the subsurface. And then EPA Rule 111D, I don't know if people are familiar with this. This is the new EPA regulation for point source power plant emissions. And what they've done is say, federally, we're going to reduce CO2 by this amount, and each of the states has their own allocation that they have to meet. And they did not include CCS in their estimates at all. And so it's not looking overly positive right now. Yeah?
What is deep waste injection?
Oh, sorry. So deep waste injection is what the old CCS wells used to be regulated under, and it happens a lot in the chemical industry. So when they make titanium dioxide, for example, they have a lot of iron left over. So they just find a saline aquifer and inject the iron underground, and they're done.
As far as for 111D, I guess if anyone in the U.S. wanted to build a coal plant, they would have to have sequestration to meet like 111D.
Yeah, they would just not build a coal plant. Like, there is no future coal will never, I don't think there will ever be another coal plant built in the U.S. again, would be my guess. I don't know for sure, but that would be my guess. So we do have a lot of sites that have been underway. There's a nice website, I think I listed it at the end, from CO2 CRC, that lists all of the different sequestration sites. So Sleipner in the North Atlantic is taking CO2 from a natural gas site and just re-injecting it underground after a separation plant, and that's partly driven by the carbon taxes associated with some of the North Atlantic countries. Snowbit is the other one that's also in the North Atlantic. They're doing the same thing. They're just taking the CO2 from the natural gas field and re-injecting it before combustion. Weyburn is an enhanced oil recovery site where they're planning to use the CO2 to get more oil. And Insula was another site in North Africa. This is the one that had induced seismicity and was shut down because of CO2 leakage. And then Gorgon is run by Chevron. It's off the coast of Australia. This is the biggest site to come online. And it's also a natural gas CO2 injection site. But you can see there's a wide array. A large fraction of these, the EOR sites, are all the crosses. You can see a lot of these across the US are enhanced oil recovery sites. So there are some companies doing pretty innovative things. One of the challenges for enhanced oil recovery is that you need a constant stream of CO2. And if you think about a power plant, they don't necessarily generate a constant stream of CO2, especially if they go down. So C12 Energy is kind of an interesting company that started in Berkeley. I heard they were moving to Denver. Their idea was to buy up a bunch of pore space in the Midwest and inject CO2 underground from the power plants and store it there, and then use it, sell it to EOR operators. And because they could guarantee this kind of constant stream to EOR, they're actually apparently profitable. They're making money off of CCS, which is one of, I think, the first companies that's been able to do that. And if you're not familiar with enhanced oil recovery, the idea is that we only get about 15%, 10 to 15% of the oil the first time we extract it from a reservoir. So they either usually go to tertiary or secondary recovery with water, and then sometimes they can use CO2. And so the idea is you would use the CO2 to get more oil and then just leave the CO2 down there, ideally. And then this comes back to another person's question, which is, do we need GCS? And this is actually a report from the recent IPCC Working Group 5 looking at mitigation strategies. And so this is the baseline. This is direct emissions of CO2 for different sectors, so transport, buildings, industry, electricity. Net AFOLU is agricultural, forestry, and other land use. And then they asked the question, okay, well, can we get to 450 ppm with CCS? And the numbers to watch are actually these numbers. These are the number of models that could come up with a solution. So could we get to 450 ppm with CCS? And the answer was yes. You can see some of the different strategies. So some models did it with big changes in electricity. Some models did changes in land use. But most of the models could actually solve the problem. And then when we go to 450 ppm CO2 without CCS, look at the numbers. Only 3 to 5 models could actually even find a solution to the problem. And so the way that I like to think of CCS is it's not a long-term solution, but it may be our only kind of short-term solution that's big enough to make a difference. Okay, so I'll say, I'm running, I guess, close to out of time, but I'll say a few things about these kind of other possibilities. Oh, you go to 5:30. Okay, I thought it was 5:15. Okay, good. So these are some of the other possibilities: mineral carbonation, and the idea here is to take CO2. You could inject it underground, or you could do this above in the subsurface, but the idea is to rely on the chemical potential of the rocks to convert the CO2 directly into carbonates instead of storing it as a fluid. And what's shown here is a cross-section. This is actually a cross-section through California. So the mountains over here to your left have a rock in them called serpentinite. How many people have seen serpentinite? No one?
That's a Jasper.
Yeah. Yeah, it's actually, they use it a lot. They use it in Stanford as a building stone a lot, and it is the California state rock. I should have brought some. It's a bluish, greenish, beautiful rock. It feels very like slippery and snaky. This is actually a piece of the Earth's mantle that has been pushed up onto the side of California, and so it formed very much out of equilibrium with the Earth's surface, and it's composed mainly of magnesium, iron, and a little bit of calcium, plus some silicate. So these are really reactive rocks. They dissolve very quickly at the Earth's surface, but they've been pushed up in slivers onto the side of California and to the sides of many other continents. So they're very reactive, and then we have the sedimentary rocks, like the sandstones that contain our petroleum reservoirs, which basically are nominally not reactive. They don't have any reactive divalent metal cations. And so the challenge really is that CO2 mineralization, the rocks that are reactive have no porosity or permeability. The rocks that are less reactive have lots of space, but they have no ability to sequester CO2. So it's a real trade-off. And so the reaction we're talking about is one between a mineral called olivine, which is a magnesium silicate. It's actually also known as peridot, the green gemstone in the bottom of this necklace. Many of you probably have some. It's also found in basaltic rocks. So if you've ever been to Hawaii, how many people have ever been to Hawaii? Yeah. Have you been to the Olivine Beach on the Big Island? Okay. So there's an entire beach made out of olivine on Hawaii that's really spectacular. So it's a neat rock. So when olivine sees CO2, it reacts to form magnesium carbonate, which is a white carbonate mineral, and amorphous silica. This reaction is 95% positive volume change, so it means you basically double the size of your products from your starting product, which is not good if you're worried about porosity. It can fill a lot of space. And then it doesn't happen very quickly. The kinetics are sort of limiting. And we've been studying a natural example of this in California. This is, I forgot to put a scale on here, but this is about a 10-meter thick vein of this magnesium carbonate forming in a rock. And this is a picture of what happens at the mineral surface. So this is the olivine, this is 50 nanometers. This is the silica-rich layer, basically this part of the reaction forming on the surface so it can passivate the surface. So these are the technical challenges. But if we go back to the question of how big and how much, I showed you the earlier diagram that suggests that it's a really big potential storage option. This is a plot. These are just dots instead of actual sizes of the rocks, but this is showing the distribution of these magnesium silicate rich rocks we call ultramafic rocks. And this is actually our field site, which is 70 miles east of here on the other side of Mount Hamilton, and it was the world's largest magnesium carbonate mine. It's one of the most spectacular examples. The only reason why it wasn't fully mined was that Austria could mine their magnesite for cheaper during World War I and World War II. So they left most of California's magnesium carbonate. So we've been studying what happens. We see these large magnesium carbonate veins. These are actually some of our experimental products where we've been looking at how fast this happens in the lab. And this is one of my colleagues, Professor Gordon Brown, in what we call the Chamber of Secrets. But these are absolutely massive magnesium carbonate veins that have formed from CO2 reacting with the rock. So Mother Nature has figured out a way to make this happen. We just haven't been able to engineer it yet. And the big challenge has been that to make this happen, it appears that we need some mechanism to fracture the rocks. And so if you think about, people were nervous about fracking and CO2 sequestration, this is even more of a challenge because we have to do hydraulic fracturing to at least get the fluids in there initially. So that's the real challenge for mineral carbonation. People think that once the reactions get started, because there's a positive volume change, they'll keep kind of creating pore space down there. It'll be sort of a self-sustaining system. The economic benefit to these mineral carbonation projects is that effectively you could walk away. When you think about the long-term storage of 1,000 years, you might not need to ensure that for these kinds of sites because the CO2 is all converted into a rock. So there's a trade-off there. So the places where people are doing this with actual CO2 from power plants, the main place is actually Iceland, where they're taking CO2 from geothermal production and injecting it back underground. There's been another pilot study in Washington. Those are probably the two main places. Australia is doing a similar version of this with above ground with mine waste. So not as much going on with basalt or mineral carbonation as with geologic storage, but it's one option. And then there's some kind of crazy things you can do with minerals. This was in the New York Times a couple of days ago. Did anyone see this? You saw it? Yeah. You saw it? Yeah. So this is the same mineral, olivine. Here they've put it on a playground, and the idea is that this mineral will just sort of take up CO2, convert it into bicarbonate, or make a magnesium carbonate mineral in the playground. And the people working on this have some interesting ideas about sprinkling olivine around. I see someone back there is amused by that idea. There have been some studies published in prestigious journals that have shown that, for example, taking olivine and dumping it in the tropics, you could change river alkalinity enough to actually influence seawater chemistry in a positive way. So it's not completely out there, but the cost of mining and everything else is a challenge.
Anything terrible about the morphology, like asbestosis, like
Oh,
aspect
boy.
ratios and things?
Yeah, so These minerals tend to be associated, ultramafic rocks turn into serpentine, and serpentine contains asbestos minerals. In fact, you were all drinking asbestos minerals a little tiny bit because our drinking water comes from Crystal Springs Reservoir, which is actually in serpentine rocks, and so they filter the water before it comes to us. The good news is that the kind of asbestos that forms in these deposits is not very harmful. It's not carcinogenic like the other kinds of asbestos. So there is a little bit associated with olivine typically. The other mineral that's often associated with olivine is chromite, which is the main mineral that contains chromium, and obviously chromium is a toxic carcinogen when it's oxidized. So there are some possible environmental downsides of these rocks, but presumably you could separate out the magnetite and chromite fairly easily, and so there's a little bit of nickel and iron in them, but that's probably good for plants anyway. So I don't think anyone has done a very good estimate or analysis of the potential toxic aspects of olivine. So I just mentioned this, the idea that we could sprinkle olivine around. And then the other part of this is a slightly more realistic endeavor, which is that instead of putting the CO2 underground and worrying about pore space, we just bring the minerals to the surface and react them with the CO2 above ground. And actually, a group here at Stanford in the Energy Resources Engineering Department did a full life cycle analysis of mineral carbonation. It was a really nice job that they did, and this is very busy. I just want to walk you through the things they included. So extraction, which is the mining part of it, the transport, the processing. You have to crush up the minerals to make it very fine grained, so it has surface area to react quickly enough. And then the chemical conversion, which is the reaction with the CO2, and then any processing that you need, and then the transportation and either reuse or disposal. And just to kind of remind you of what the challenge is for this, this is a plot of the concentration of magnesium and pH. And so if we think of a water with CO2 in it, we're basically at this pH range where magnesium in solution is favored. And you basically have to add alkalinity to form the magnesium carbonate mineral. And so the company that you guys looked at, New Sky, Cholera, that's been everyone's challenge for doing this to make products that contain calcium carbonate, is that you have to add alkalinity, and getting that source of alkalinity is challenging. So these guys did a full analysis of the carbon dioxide emissions associated with each step in the process. And the big one here is the chemical conversion, and that, I believe, is all associated with the capture. And what they did, if I remember correctly, is they tried to scale everything by 1,000 tons per day of CO2, which is what they thought they needed to make a difference. And so finally, they looked at a bunch of different strategies. So the idea here is we could use olivine, or we could use waste slag from metal refining. We could use coal fly ash, which also has a lot of reactive components. So we could use a number of different waste streams and convert it into carbonates. And on the whole, the olivine, which is shown right here, is the most favorable in terms of, if this is for 1,000 tons sequestered, this is the loss from the industrial process.
What's the difference between the A and the B?
The A is, this is a really key assumption, that they needed to estimate how much alkalinity was produced or how much sand and gravel. So A is how much alkalinity is produced in the US total. B is based on how much sand and gravel we produce. So it's the difference between like 20, I might have written it down, 20 megatons, 18 megatons per year in A and 760 megatons per year in B. So there's some pretty big assumptions in here. The other one isn't actually in the extraction. It's a big, mining is an expensive, costly effort. So, but there are some companies doing this. So Clean Sky was one. Cholera is another one, who I believe Brett Constance, who was the founder, came last year, and they've
probably find YouTube, but
yeah,
it was a neat lecture.
they're a neat company. They've been developing calcium carbonate products to make cement. So I believe, if I remember correctly, the sidewalk at the corner of Sand Hill and Foothill is made of their cement from their process. And they've also been making different tiles and pottery and benches out of calcium carbonate. So they have a unique process for making products out of calcium carbonate. And their trick for getting the alkalinity is to use an electrochemical process that generates both a precursor to PVC and sodium hydroxide. And so that's how they get the base to make the calcium carbonate. And actually, that technique has turned out to be more beneficial than this approach. So they've kind of focused more, I think, on the electrochemical side of their business than the CO2 product side. So I'll say one last word about sort of the crazy idea. What are the crazy things we could do if we had the technology? And this is the idea of sort of subsurface cycling of CO2, or basically converting CO2 into a reduced form and storing it in reduced environments. And the idea is that if we put CO2 down into these petroleum reservoirs, we know that they're reducing because the petroleum has been there for millions of years. So if we can make the CO2 into something that's more reducing, it should stay there, and then maybe we could actually get beneficial products in terms of either stimulating subsurface microbial communities or making actual useful products. And this is a pretty complicated diagram. I'm just going to explain the basics. So this is the log of aqueous hydrogen, and this is basically just a proxy for redox conditions. So if you guys are chemists, you can think of EH or reducing conditions. So in this plot, very oxidizing conditions are down here. So the Earth's surface is somewhere in here, and then this is just temperature. And if we look at petroleum reservoirs, they plot up here. So they're quite reducing. And these black lines show the mineral reactions that actually control the redox conditions in these reservoirs. And the red lines show the ratio of CO2 to acetic acid in these reservoirs. And we're just using acetic acid as a proxy for reduced organic carbon. And so the idea is that CO2 would come down and it would attach to a mineral surface. And the mineral surface would either catalyze or at least promote the reduction of CO2 to another organic molecule. In this case, we made formate. So we've been able to get this to happen in the lab. We haven't been able to do it in the subsurface. But the idea is that if this is where petroleum reservoirs sit, and you add CO2, you basically come down this direction, and there's now a chemical potential that would drive you back up to these initial conditions and convert the CO2 back. So there's a lot of redox conditions, redox potential down there to help us. It's really the technological side of the catalysis of the CO2. And there's groups here that are doing electrochemical CO2 reduction, and we might be able to learn from some of their materials and actually facilitate. Mm-hmm. Yeah. They use really things that are really similar to natural minerals. Okay, so that's just kind of an overview. I put up some different reading. So if you're interested in more about the CO2 sequestration, Sally Benson, who's here at Stanford, has a nice review paper in the journal Elements. Jen Wilcox wrote an amazing book on carbon capture. She's also here. And then Klaus Lackner has been thinking a lot about the mineral carbonation side and been very vocal that is, in his opinion, I think one of our only real viable strategies. But the new IPCC working group report is worth taking a look at. And then some of the CO2 capture project websites are listed here. And I think that's it. Yeah.
Klaus Lackner is at Columbia, right?
Yes.
That's impressive.
Yeah.
Well, thank you so much.
Sure. Yeah.
Questions? Want to see?
Yes.
Is research being undertaken on trying to find ways to sequester some of the other harmful emissions from fossil fuels, like methane and SOx and NOx and mercury and stuff like that?
Yeah, that's a great question. A lot has already been done on the SOx side. And in some of these cases, people have looked at co-injection of H2S with the CO2. The real issue there's not so much a problem once it goes underground. The issue there seems to be more with the pipelines and the pumping apparatus. So one of the sites I mentioned in Iceland is actually co-injecting H2S and CO2 because the geothermal wells produce a lot of H2S. As far as what to do with the H2S byproduct, I think Clear Sky, we keep forgetting their name, is capitalizing on that. Mercury, people have been looking at it. It's more of an issue with coal, I think. But people have been looking at develop better methods to scrub mercury from coal. And actually, Jen Wilcox, that's one of her specialties, is looking at mercury. So does that, okay. Yeah.
Capture methane?
Can you capture methane?
Do similar.
You could, I suppose. I don't know that anyone is concerned with methane.
Oh, as
Is
it gets
it-
released from permafrost.
From-
Yeah, there's some interesting schemes. But I
Is
don't
there-
know.
okay.
Flaring, like when you're flaring,
Yeah.
natural gas flaring, or just
Well, then you're just producing CO2.
Which is not as potent a greenhouse gas as methane.
Right.
oh yeah, yeah.
Yeah, I mean, I think the natural sources, I agree, are a big problem. I don't know how much the industrial emission of methane is. It seems too valuable. Why would you want to let it go, or at least burn it off? I think. With all of these gases, they're hard to sorb. That's one of the challenges with any of them is the sorbent part. So, yeah.
How much is modeling being used to sort of examine the cost of the Earth to, in others, like determine like their appropriate pressure to put the CO2 in? Because like for instance, you were given an instance of like the CO2 coming back up. Like what was like led to that? Was it like the Earth crust did something weird that they didn't expect was going to happen?
Yeah, so that's a great question. I didn't show any model simulations. The oil and gas industry, and actually even people here at Stanford, there's been decades worth of work on what they call reservoir simulation, which is simulating how fluids move and how the pressure changes. And they're very advanced simulation tools. They're constrained by seismic measurements at the site usually. I believe what happened at Insula was that there was a sort of low permeability unit that they didn't know had a low permeability, and the pressure started building up, and instead of just stopping the injection, they kept going, and I believe that was what caused the problem. But there is substantial modeling being done, and we've been doing a lot of modeling on the effects of leakage and the idea of putting reactive barriers down that would react with the CO2 and stop it from moving up any further. So Sally Benson over in ERE is one person who's worked a lot on that, and there's a whole group over there that it's really impressive, the knowledge and the computational ability that they have to solve these problems. So.
Thank you again. This was terrific.
Yeah.
Appreciate it.
Yeah, it was fun to put this together.